In 1948, a 32-year-old engineer at Bell Labs published a paper that quietly set the speed limit of every internet connection on Earth. Past, present, and future. Every Wi-Fi packet, every satellite call, every MP3, every line of an AI model. All of it sits underneath one equation, written by a man who also rode a unicycle while juggling 4 balls down the halls of Bell Labs. How did one playful tinkerer from a small town in Michigan turn the word information into a hard number? Before 1948, the word information meant everything and nothing. Newspapers carried it, telegrams carried it, gossip, smoke signals, shouted warnings, all of it was information. But no engineer could tell you, mathematically, what they were transmitting, or how much of it. Imagine trying to engineer a national telephone network without knowing what the basic unit of the cargo is. That was the world. Engineers had pieces of the puzzle. Nyquist in 1924 knew that signal speed scaled with bandwidth. Hartley in 1928 suggested measuring information as the logarithm of the number of possible messages. They had pieces, they didn't have the framework. What was missing was a particular kind of mind, someone who treated mathematics the way a child treats a Lego set. To find that mind, we have to drive north, to a small town in Michigan in 1916. Claude Elwood Shannon was born on April 30th, 1916, in Petoskey, Michigan. He grew up 40 miles south in a town called Gaylord, population 3,000. His father was a probate judge, his mother, the principal of the local high school. And somewhere far back on his mother's side, a distant cousin named Thomas Edison. Young Claude only learned about the family connection years later, but Edison was already his hero. At 12 years old, Claude strung a private telegraph wire between his house and a friend's, half a mile away. The wire was just a length of barbed wire fence. The Morse code traveled along it perfectly well. He repaired radios for the neighborhood. He built model airplanes. He built a radio-controlled boat. His older sister Catherine, a math teacher, fed him puzzles and codes, and he ate them as fast as she could write them. 2 themes lock in here, in childhood, and they will run for the rest of his life. 1. Play and work are the same thing, and they always will be. 2. Electricity to him is not a utility, it is a medium for messages. In 1932, at 16, he enrolls at the University of Michigan. 4 years later, in 1936, he graduates with 2 bachelor's degrees at once. 1 in mathematics, 1 in electrical engineering. He is 20 years old. Somewhere in those Michigan years, in a philosophy course, he meets the algebra of George Boole. Boole, writing in 1854, had built an algebra not of numbers, but of truth and falsehood. And, or, not. 80 years before silicon, Boole gave Shannon the language he would later pour into copper. In the fall of 1936, Shannon takes a job at MIT, operating Vannevar Bush's differential analyzer. It is a room-sized mechanical computer. Gears, shafts, integrators, and a chaos of electrical relays controlling the whole thing. And as he sits there, operating that chaos, 21 years old, he sees something nobody else has seen. A relay is just a switch, and a switch is just a true or a false. And becomes 2 switches in series. The lamp lights only when both close. OR becomes 2 switches in parallel. The lamp lights when either one closes. NOT becomes an inverter. The lamp blows when the input is off. Wire 3 switches as A and B or C, and the lamp obeys the algebra exactly. Any Boolean expression can become a circuit. Any circuit can become a Boolean expression. They are the same thing. On August 10, 1937, he files his master's thesis at MIT. It is titled, A Symbolic Analysis of Relay and Switching Circuits. He is 21. Howard Aiken, decades later, will call it the most important master's thesis of the 20th century. Every digital chip on Earth, every CPU, every phone, every server is a descendant of those relays. 3 years later, in 1940, he completes his PhD at MIT, but not in engineering. His doctoral thesis is in mathematical genetics. He wrote most of it at Cold Spring Harbor over a single summer. He was already restless. The world was about to give him something to focus on. It is December of 1941. Pearl Harbor is bombed. America enters the war. And a 25-year-old mathematician walks into a building in Murray Hill, New Jersey. In 1941, Shannon joins Bell Labs full-time. The United States enters the war that December. Shannon is pulled into classified work, cryptography. His most important wartime result was a mathematical proof, that the one-time pad is unbreakable. If the key is truly random and used only once, no amount of computation can recover the message. That classified 1945 memo would become the public paper, Communication Theory of Secrecy Systems, in 1949. In the spring of 1943, Alan Turing visits Bell Labs. He and Shannon take tea together several afternoons a week in the Bell Labs cafeteria. They cannot discuss their classified work, so they talk about something else, machines that could think. By the war's end, Shannon has the question that will define his life. Forget meaning. Forget what a message says. How much uncertainty does it resolve? Imagine 2 coins. The first is fair, heads or tails, 50-50. The second is rigged, heads 99 times out of 100. Flip both 20 times. The fair coin jumps around. Every flip is a small surprise. The biased coin? Heads. 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 You knew it was going to be heads. The biased coin carries almost no information. So define surprise this way. An event with probability p has surprise equal to minus log p. A certain event, probability 1, has 0 surprise. You knew it would happen. A 1 in a million event has a lot of surprise. You did not see it coming. Now ask, on average, how surprised are you per flip? Take each outcome's surprise. Weight it by how often that outcome happens. Add them up. That's it. That's the formula. Shannon called it H, the entropy of a source, the expected surprise of one message. H equals minus the sum over every outcome I of p sub I times log p sub I. Plug in the fair coin. Both probabilities are 1/2. The arithmetic resolves to exactly 1 bit. That is the unit of information. 1 bit equals the surprise of a single fair coin flip. Shannon's colleague John Tukey suggested the name. Bit, short for binary digit. Plug in the biased coin, 99 and 1. The entropy collapses to about 0.08 bits, 12 times less information per flip. Why a logarithm? Because 2 independent flips should give twice the surprise. Probabilities multiply, but the log of a product is a sum, so information adds up, exactly as it should. A six-sided die, log base 2 of 6, about 2.58 bits. The English alphabet, if every letter were equally likely, would be about 4.7 bits per letter. But English isn't random. After accounting for patterns and redundancy, real English carries only about 1 bit per letter. That is why a page of English compresses so well. Most of what's there you could have guessed. And the deepest claim of the paper, H is the absolute lower bound on how compactly you can encode a source. Every zip file, every JPEG, every MP3, they are all squeezing toward this number. You cannot beat it. Shannon proved you cannot beat it. This is the picture Shannon drew on page 2 of the 1948 paper. Source, encoder, channel, decoder, destination. And in the middle of the channel, noise, static, interference, bits getting flipped. Every communications engineer alive still carries this picture in their head. The engineers of the 1940s asked an obvious question. If the line is noisy enough, surely some of your message must be lost forever. Shannon's astonishing answer was, no. Define the channel's input as X, the output as Y. Each has its own uncertainty, its own entropy. The mutual information between them is how much knowing Y tells you about X. Shannon defined the channel's capacity as the maximum of that quantity over every possible way you could choose to encode the input. C equals the max of H of X, the uncertainty before seeing the output, minus H sub Y of X, the uncertainty that remains after. And then he proved his coding theorem. Below C, you can transmit with as small an error rate as you like by encoding the message cleverly enough. Above C, you cannot. No cleverness saves you. For the most important case, a band-limited channel with Gaussian noise, Shannon gave a formula. C equals W log of 1 plus P over N, the Shannon-Hartley theorem. W is the bandwidth, how wide a slice of frequency you have in hertz. P over N is the signal-to-noise ratio, how loud your signal is compared to the noise. And the log is what makes the curve cruel. Plot capacity against signal-to-noise ratio. The curve climbs, but slowly. Double your power. You buy yourself just 1 extra bit per second per hertz. This is why engineers fight so hard for spectrum. Bandwidth is cheaper than power. A channel's capacity is like the maximum legal weight on a bridge. Pile cargo on as long as you stay under it. 1 ounce over and the whole thing collapses. Every wire, every radio band, every fiber, every spacecraft uplink, they all sit at the bottom of this curve, climbing toward C. This is not a theorem about telephones. It is a law of nature about communication. In 1949, Shannon marries Mary Elizabeth Moore, Betty, a numerical analyst at Bell Labs. She would help him build many of the inventions that come next. The first one is a mouse. In 1950, Shannon builds Theseus, a small magnetic mouse that finds its way through a maze. On the first run, Theseus bumps into walls, backtracks, and slowly finds the cheese. On the second run, the same maze, it runs straight there, no mistakes. Theseus learned. Its memory was built from old telephone relays. This was 1950, decades before anyone called it machine learning. Marvin Minsky, then a young researcher visiting Bell Labs, suggested another idea to Shannon. A box whose only function was to turn itself off. Shannon built it, put it on his desk, flipped the switch, a small mechanical hand emerges, flips the switch back, and disappears. Arthur C. Clarke later called it the most useless machine ever invented. He meant it as a compliment. Down the corridors of Bell Labs, Shannon could be seen riding a unicycle while juggling 4 balls. He took juggling seriously enough to write a theorem about it. B over H equals D plus F over D plus E. B is the number of balls, H is the number of hands. D, F, and E are the times in hand, in flight, and empty. The number of objects you can juggle is bounded by physics. He proved it on paper. He even built a juggling machine, 3 steel balls, 3 motorized arms, bouncing them off a drum forever. His basement in Winchester, Massachusetts became a toy room of inventions. Flame-throwing trumpets, a rocket-powered frisbee, plastic foam shoes for walking on water, a chess-playing machine, a juggling robot. The playfulness was not a side of Shannon. It was Shannon. The same mind that turned uncertainty into mathematics, treated machines and puzzles as things to play with. In 1956, Shannon returns to MIT as faculty. He becomes the Donner Professor of Science. He teaches sparingly, he publishes less and less. But by then, his ideas have a life of their own. Over the next 70 years, his ideas spread through every digital technology the world would build. Zip files, FLAC audio, lossless compression, Huffman coding, built directly on Shannon's JPEG, MP3, AAC. Lossy compression, throwing away exactly the bits the ear and the eye won't miss. Wi-Fi, 5G, every modem you own, all operating right at the bottom of the Shannon-Hartley curve. Voyager 1, launched in 1977, is now in interstellar space. It still beams telemetry back to Earth, using error-correcting codes whose feasibility Shannon proved. Every CD, every Blu-ray, every hard drive. The bits you read today were corrected by Shannon's mathematics. And every modern AI model, every transformer, every language model, is trained by minimizing a quantity called cross-entropy loss. It is, almost letter for letter, Shannon's H, repurposed. 78 years, one paper, still running underneath everything. Shannon developed Alzheimer's in his last years. He died on February 24, 2001, at the age of 84. He never quite saw the internet take over the world, but the internet was already running on his math. Shannon did something most scientists never do. He took something the world thought was unmeasurable, information, surprise, uncertainty itself, and made it a number. He could only do that because he treated mathematics the way he treated juggling, as a puzzle, as a toy, as a thing to take apart with your hands and put back together better.